So last time, the last thing we were doing, we were talking about linear half spaces as a set of classifiers. So I can denote it by half spaces of dimension n. And this is the set of all classifiers that are just weights over the coordinates of the point compared to some threshold. So it is the class of all h, w, b, such that w belongs to Rn, b belongs to R, and h, w, b of a point x is defined as the sign of the vector sigma wi of the vector sigma wi xi plus b I goes from 1 to n. So this is, you see, if I can write a linear half space as saying, I look at, if I have a point x1, x2, and I have some weight vector, which is, say, 3, 5, and b equals 1, then I can say I'm looking at h, w, b of my point x1, x2 is just the sign of 3 times x1 plus 5 times x2 plus 1, which is the same as saying I look at this half space, right, that cuts here at -1 and has the angle 5/3, and I mark as +1 all the points above this line and as -1 all the points below the line. So this is a linear separator. It's just a nice algebraic way of defining when you are above or below a linear half space. This is in R2, and this generalizes it to Rn. And yes?
I could generalize the line, like above the line.
Yeah, so I mean, algebraically it's nice. I don't have to draw pictures. But if I try to draw pictures, what it means is you have some kind of a subspace, almost a subspace, right? You have, so if you are in R3, you have some kind of a plane, and which cuts. So you can think of it as we have some kind of a plane that cuts, starts with the ceiling there, goes right here, and you are either above or below this plane in R2, in R3. So you have a two-dimensional linear plane, and it cuts the space R3, and you check whether a point is above or below it. But the algebraic definition is more useful, and as I mentioned last time, the algebraic definition can be given a very clear intuitive meaning. One of the things that when we search for a classifier, sometimes we also want a classifier that can be explained, that have explanatory power. And this can be well explained, because remember that the xi's are the features of my point. So if I'm talking about the papaya, and I want to decide whether a papaya is tasty or not, and here I have the softness, and here I have the color, and I get a half space that looks like this, and so I have some coordinate times the softness plus some coordinate times the color should give me some result. I can interpret as saying the higher the weight wi, the more important is this feature. Small changes in this feature makes much more of an effect over the outcome than small changes in the other feature. So if I want to find a linear classifier like this for the predicting whether by the age of 50 you will have a heart attack or not, and my coordinates are your weight, how much exercise you do, your blood pressure, whether your parents had heart attack or whatever, and I give you such a linear classifier, the weights can be read as saying, you know, the highest weights is whether you exercise or not. This is the thing that will mostly affect whether you will be above or below this threshold that predicts heart attack. So it has a very clear explanatory power. I can read off it kind of how much each component, how much each feature contributes to the outcome. So these are very common classifiers. They have other advantages. Another nice advantage of having a classifier like this is that if I do, so again, we are trying to learn this classifier. So we are getting points which are marked as plus, and we are trying to find the best linear classifier that separates the pluses from the minuses. Right? So we are now, so assume that we concluded that this is our classifier. And now I get a new patient. And I want to decide what do I predict. Do I predict it's going to be minus, or do I predict it's going to be plus? So, of course, if the new patient, I want to predict whether he's going to have a heart attack or not, the speed of prediction is not so crucial. But there are applications of machine learning in which the speed of prediction is very crucial. So if, for example, I'm collecting all kinds of information about the driver. There are now devices like this that have a camera that looks at the driver, and it checks whether your head falls back and forth, whether your eyelids are flapping, whether you are moving at all or not. And it calculates some kind of a prediction whether you're falling asleep or not. So now I have this linear predictor, or some predictor, and now I have the measurements of all the features of the driver, and I want to predict whether he's falling asleep or not. Now, in such a case, the speed of prediction at prediction time is very crucial. I cannot allow myself that I measure all the components of my driver. Now I calculate for 10 seconds, and then I decide whether to raise an alarm because I suspect that my driver is asleep. If I wait 10 seconds for computations, my asleep driver may not be able to hear my alarm. So in some applications, the speed of prediction is very crucial. And with such a predictor, we can do it very quickly because we calculated the weights. That's our prediction. Now we get a new point, which is the vector of the xi's. All I have to do is do the dot product. And I can have it really a chip that does it in no time, practically. Just compute the dot product of these two things. So one and other advantage of linear predictors is that they can be computed, the outcome, once I have my weights. Once I chose my hypothesis H, and I get a new point and I have to predict, I can do it really, really fast. And we use it even inside hardware, inside the work of chips, to predict what is going to happen. I mean, I don't want to get into this, but it can be done so fast that it's being used in chip design to predict what is the next action of the chip going to be. OK, so there are lots of advantages to half-space predictors, and it's going to take a play a significant role in the course. Why do I tell you all this story? In our context, we were talking about the VC dimension, and I want to talk about the VC dimension of this class. Now, so it's just an exercise with VC dimension, but it's an exercise on a very practically relevant class. And to make things a little bit easier, and then we will see that it doesn't really make a difference, let us restrict our attention to what we call homogeneous linear classifiers. And by homogeneous, I mean that we assume that we fix B to be 0. So it's the set of all H, W0, such that W is in Rn. I fix the threshold to be 0. So it just classifies linear separators that go through the origin. But we will see that this is not a significant restriction. But it makes the analysis easier. OK, so we restrict our attention to such classifiers. And now I'm asking you, what is the VC dimension of this class? So the question we want to address is, what is the VC dimension of H n half spaces n that goes through 0? So we can try it. We can try it in R2, but what will it be in general? So let's start with R2. What do you think is the VC dimension of the class of all half spaces or linear separators that go through the origin in R2? Let's do it bit by bit. Can you shatter 1 point? What does it mean to shatter 1 point? I have to show you one classifier that classifies this point as plus, and another classifier that classifies this point as minus. Can we do this? Of course we can. I'll pick 1 point here. I'll take one classifier that goes above it, and other classifiers that go below it. Could we shatter 2 points? OK, so anybody volunteers to explain to me where should I put the 2 points so that they could be shattered? Yes? What? I put them on one of the axes and I try to shatter them. I'm going to have a hard time. Why am I going to have a hard time? Because I cannot have a line that goes through the origin that will pick one of them and miss the other. So how should I put 2 points if I want them to be shattered? Yes?
If you have 2 points, one a little bit above the other, you can have one line that is over both of them, one that's between the two, and then one that's under both. OK, so what? Yeah, but I need more than that. Oh, so I can take both of them. This line will give me the labeling +1, +1 on these 2 points. Right? This line will give me the labeling +1, -1. 1 point is below, 1 point is above. This line will give me -1, -1. Both are below. So what am I missing? I'm missing a one that will say this is negative and this is positive. How can I do that? I can. Any suggestion? Yes?
Well, are you able to put them in the other quadrant?
I want what?
They have to be in that quadrant, right?
I picked these 2 points. I want to show that they're shattered. And I claim that they are shattered, yes. I negate the coefficients. Because the half space is not, I mean, if I negate the coefficients, you see we have this algebraic definition here. If I negate the coefficients, just reverse the sign of them, then what was negative below will become positive now. What was positive below will become negative now. If I have a half space, if I have this line, it really gives me 2 potential separators. That one that says plus here and minus here. But if I flip the coefficients from minus to plus, I get the one that will give me plus here and minus here. So by flipping the coefficients, I will also get the +1, -1, the opposite of this guy, and I'll have all possible ways of splitting these 2 points. So I will conclude, yes?
If we just have 1 point and we put it in the origin, then we couldn't shatter it, right?
What?
If we just have 1 point and we put it in the origin.
If I had 1 point,
And we put it in the origin.
then I have trouble. I don't know what to do with it.
But then we couldn't shatter it, right?
What? We
Then
couldn't?
shatter it. If we just have 1 point in the origin, we
The-
couldn't shatter it. Because it
I-
would always be 0.
I could not what?
We couldn't shatter it. 1 point.
I could not shatter it. Oh, I could not, maybe I could not shatter it. It's a question of definition of how do we do with the point that goes through the line, right? But the VC dimension depends on the existence of shattered points. So the fact that there are 2 points that are not shattered doesn't hurt the VC dimension. The VC dimension just asks, do there exist 2 points that are shattered? 2 points that are not shattered don't hurt us. But now we know that the VC dimension of what? Of half spaces in dimension 2, which are homogeneous, is at least 2, because we could shatter 2 points. Now, if we want to show that it's not more than 2, we have to show that no 3 points can be shattered, which is becoming a little bit more delicate. Can you show me why no 3 points can be shattered? Yes?
Because in order to shatter that set of points, you need to have like no 3 collinear points with the origin of those 2.
I don't know. So I take 3 points, and I have to show that I cannot shatter them. Yes?
No 2 can be on the same line with the origin, because you can't shatter 2 points which are...
OK, they're not on the same line with the origin. OK.
So then you can take it clockwise.
I can do all kind of tricks and there's consideration.
Take clockwise orientation.
OK. I mean, I'm not asking you to do it. I'm just saying, you see, it is getting harder already in dimension 2. But I want to figure out the VC dimension of half spaces in dimension n. So if we are already having trouble in dimension 2, what will happen in dimension n, right? It's going to get harder and harder. Yes?
So start from the 2 points, and then show that no matter where you add a third point, there's no way of doing the split. And I think like kind of to do that intuitively, you end up showing that you can't do this like flip of orientation to shatter the whole set.
Anyway, I mean, what I'm saying, I really don't feel embarrassed by not coming up with the answer, because it's getting complicated in lots of cases, and it's only dimension 2. And I want to give you an answer for any dimension. So the trick is that instead of applying our geometric interpretation, which completely gets lost in high dimension, we have to rely on the algebra. The algebra is reliable. So the algebra, we just do manipulations. We don't need to try to visualize it. Visualization is limited. OK? So I claim that indeed the VC dimension of half spaces, linear half spaces going through the origin in dimension n is exactly n. So let me make this claim, and let me show you an algebraic proof. So I make here a claim that the VC dimension of half spaces going through the origin in dimension n is just n, and actually the VC dimension of half spaces in general without this restriction is n plus 1, and this is for every n. And I will prove the first statement and leave the second statement for the next assignment. OK? So, and what I'm claiming is that in such things, when we have high dimension, we really cannot rely on visualization, and we have to resort to the algebra. So the proof consists of 2 steps. The first step is to show you that the VC dimension is at least n. So the first claim, claim 1, the VC dimension of half spaces, homogeneous half spaces in dimension n, is at least n. What do I need to do in order to establish claim 1? I need to give you an example. You remember, if you want to show me some VC dimension to show that it's at least something, give me an example that this is shattered. And I need to give you an example in Rn, so I need to describe these points algebraically. Okay, so proof of claim 1. Let consider the points E1 up to En, where E sub I is the vector that is all zeros, 1 in the i's coordinate and zeros in anywhere else. So we are considering the unit vectors, right? So this could be E1, this could be E2 in R2. I'm just looking at the points which are sitting on the axis at distance 1. And I'm claiming, of course, this set contains n points. And I want to show that it is shattered by homogeneous half spaces. That I can shatter this in any dimension. OK, so how do we show it is shattered? So to show it is shattered, pick any subset B of E1 up to En of my vectors. And now I have to give you a vector element HB. Let HB, now I have to give you some coordinates, W1 to Wn, that will classify each of the members of B positively and each of the members of this set which are not in B negatively. So what do you suggest? What are going to be my coordinates? It is going to be coordinates W1 up to Wn, but how do I define Wi? Yes? Right. Very nice. It is 1 if EI belongs to B, and negative 1 if EI is outside B. So I give you a vector of weights which are -1 and +1. What will happen if I take a point in B? Then I have the sum for a point in B. What happens when I take the sum of Wi xi W1 xi, but what is xi? Xi is the coordinates of this guy. Right? So we can write it like this. We can write it as the dot product. Are you familiar with the notation of a dot product? So we know that HB of any point x is the sign of the dot product, the vector WB, the vector x. Right? The dot product of the two vectors is the sum of their pointwise coordinate multiplication. Is that clear to everybody, this notation? Right? So in general, the dot product of x1 to xn, y1 to yn is the sum of I goes from 1 to n of xi wi, yi. In our case, one vector is this vector of weights. The other vector is my vector of the point. And now I take my weight vector, WB. So WB looks like 1, 1, -1, -1, 1, 1, and so on. That's the vector WB. It is 1 inside B and -1 outside B. And I take the dot product with some vector EI, which is 0, 0, 0, 1, 0, 0, 0, and so on. So what will be this dot product? If I take a vector EI, and I take away my weight vector WB, and I do the dot product, the inner product. What do I get? Yes? Either 1 or negative 1. The outcome will be just the coordinate Wi. Because only the i's coordinates count. All the other coordinates zero out because I have here zeros. The only coordinate that survives is the coordinate that matches this one, which is the i's coordinate. So it's the coordinate Wi. But I chose Wi such that it will be positive if I'm in B, and it will be negative if I'm outside B. Right? So we conclude that for all EI in E1 to En, the vector HB applied to EI, the result that I will get will be 1 if EI is in B, minus 1 if EI is not in B, because that's exactly how I define the weights, and the result of the dot product will be just the weights. So we showed that the set is shattered. I can separate every subset B. And again, we see the advantage of doing things algebraically because we don't have to draw higher dimensional pictures and imagine those half spaces and strain our minds too much. We just have to follow very simple calculations. Any questions at this point? Yes?
Will EI be always like this? Like there's only going to be one single one?
What do you say?
If the vector EI, will it always have a single one?
Yeah, I mean, that's what my definition. I wanted to show you that this set is shattered. That was my set A. I wanted to show that the VC dimension is at least n. So in order to show the VC dimension is at least n, I had to pick at least one set of size n which is shattered. I can choose which one. So I choose this set because it's easiest for me to show you that this set is shattered.
We could use the same for n plus 1 as well.
What do you mean n plus 1?
If you want to prove that n plus 1, it can also, at least it's n, it can be greater than n as well, right? The VC dimension.
I want to show that the VC dimension is exactly n.
Okay.
So I want to show that no sets of size n plus 1 is shattered. So if we translate back to dimension 2, what I showed you now is that if I pick this point, 1 here and the point 1 here, I can shatter this set. So I showed you the VC dimension at least 2 because I gave you an example of a pair of points which is shattered. If I want to show the VC dimension is not larger than 2, I have to show you that no matter where you pick 3 points, they will never be shattered. So that's what we should do now. So we proved the first part. The first part, the VC dimension is greater or equal than n. Now I want to show you that the VC dimension is not more than n. So now I have claim 2. The VC dimension of the homogeneous half spaces in Rn is at most n. So to prove claim 2, proof of claim 2, I need to show you that given any set A equals x1 up to xn plus 1 of n plus 1 or more than n points. So it doesn't necessarily have to be an n plus 1 of more than n points in Rn. A cannot be shattered by the class of homogeneous half spaces. So the positive, I have to just give you one set. I'll pick my easiest one to shatter. For the negative, I have to show you that no matter how hard you try, you will never find a set of size n plus 1 that's shattered. And again, the only way I can address it, I mean, we're in high dimension, I can't draw pictures, I can't even imagine how it looks. My only tool is algebra. Yes?
Use topology.
I could try to use topology, I could try to use many fancy things for mathematics. Simple algebra suffices here. Now, what's a simple algebra? All of those points, there are vectors in Rn. And we know that the linear dimension is a linear space. What is the dimension of Rn? N. So what I'm saying here is since the linear dimension of Rn is n, for any n plus 1 vectors x1 up to xn plus 1, there exist coefficients a1 up to an plus 1, not all of them 0, such that sigma ai xi is 0. I goes from 1 to n plus 1. You remember, now I rely on assuming that you remember something from linear algebra. If I have a vector space and it has dimension n, then whenever I take n plus 1 vectors, I can find the combination that will get to 0. If you don't like abstract linear algebra, just recall that I give you n vectors in Rn. You can solve this equation that find coefficients that will make all of them equal 0. Yes?
Set has to be linearly independent.
What? No. I'm claiming that any set of n plus 1 points is linearly dependent. No matter what set you pick. The maximum independent set is of size n. So any set of n plus 1 points is linearly dependent. Linearly dependent means that I can find a combination that will equal 0. OK? Just because if the dimension is n, every set of larger size is linearly dependent. And that's the definition of being linearly dependent. Because I have to show you that every set cannot be shattered. So if that's the case, now I will divide, let P subset of 1 to n be the set of coordinates for which ai is greater than 0. P for positive. And n, another subset of 1 to n, will be the set of coordinates for which AI is less than 0. Since not all of the coefficients are 0, I know that it cannot be that both of them are empty. Okay, so let's see what did we do here. You gave me n plus 1 points in Rn, and you challenged me to shatter them. And I want to show you there's no way they cannot be shattered, right? So I take those n plus 1 points, x1, x2, up to xn plus 1, and I now divided them somehow into two sets, the set P and the set N. Yes? N subset of n plus 1, right. Thank you. I have n plus 1 points. Thank you. I had those n plus 1 points. I have a linear combination that equals 0. I look at the coefficients, and if the coefficient is positive, I put you in set P, and it's negative, I put you in the set N. I don't care about 0 coefficients. I know that at least one of them is not empty. Now, because the total combination is 0, I can conclude that the fact that sigma ai xi, I goes from 1 to n plus 1, is 0, that's what we know from the linear dependence, implies that the sum of ai xi I in P equals the sum of aj xj j in n, when I take here absolute value. See, if I add both of them together, I get 0. So it means that if I take all the negative coefficients and move them to the left-hand side, the two sides will be equal. You see, this is just the sum of the points in P minus the sum of the points in Q, in N. So I can take the minus the sum of the points in N, move them to the other side. So I get that the sum of the coefficients with the positive coefficients equals the sum of the points with the negative coefficients. But now, since I moved them to the other side, the negative coefficients became their absolute value. Don't give me this look. It's not so complicated. Yes?
Is there a proof that AI xi is always 0?
The proof that there are AIs such that this will be 0 is just a claim that every n plus 1 vectors in Rn are linearly dependent. Linearly dependent means I can find a combination that will zero them out. That is just saying the xi's are linearly dependent. There is a combination that makes them 0. Now we are almost done. We have to recall what we are aiming for. I wanted to show that this set cannot be shattered. To show you that this set cannot be shattered, I have to give you a subset B such that no H can cut B from the complement of B. You remember that's the definition of shattered. So now I will pick my set B. Let B be the set of all xi such that I is in the set P. So here is my set B. This is now, I call it B. All the points that went into the set P. Now I claim no linear half space can give me a positive sign on every xi here and a negative sign on every xj here. Are we clear what we need to show? Right. So now just think of it. If I have assume by way of contradiction that I had some HB that does it. So HB on each of those points will give me something positive. So if I apply HB to the sum, it will be a sum of positive coefficients times positive when I apply HB to x. So this will be positive. Right? And similarly, if I apply HB to the negative signs here, I need to get something negative. So I'll get that something positive equals something negative. Right? If HB gives me a negative sign of each of those xi's, they have positive coefficients, all of them are negative, HB of this will be negative. If HB gives me positive on every point in xi, HB on this will be a sum of positive coefficients, positive numbers, it'll be positive. So I'll get the positive number equals a negative number. And that will be a contradiction. So let me write it down. So HB, if I apply HB to this, I can think of it as a point. It's a sum, but the sum of points in Rn, I can just calculate the vector and get a point. So I'll apply HB to sigma I in P, AI, xi. I'll just look at the sum of those points as if it's a new vector. I can add vectors in Rn, right? And I can apply HB to this new vector. So what do I get because of linearity? It is the sum of AI, I in P, of HB applied to xi. Because HB is just a linear, I mean, I'm writing HB of this instead of writing the dot product. I could also write it with dot product. HB has coefficients, W's, and it's a dot product. So I have this property. Now, since HB separates, all of those members are in B. So all of those are positive. All of those are positive. So this is going to be greater than 0. HB on every point that belongs to B should be positive. On the other hand, HB of sigma j in n aj xj is the same as the sigma of aj j in n of hb applied to xj. Now they are all negative because the points in n are outside B. For points outside B, I want to get here negative. So I get a sum with positive coefficients of negative numbers. This should be less than 0. So now I got a contradiction. Why is it a contradiction? Because this point and this point are the same. They are equal. So how can it be that when I apply h to it once, I get positive? When I apply it again to the same point, they are equal. I get a negative result. So we got a contradiction. Yes?
I don't really see why they're equal. Like, how are x defined? I mean, a's are equal.
What?
I'm not sure what x is.
Okay, but try to formulate your question, and I'll be happy to address it.
So x's are different.
X's are different points, the points that you supposedly were trying to shatter. But what I'm saying, the key point is this linear dependence. That there exist coefficients ai such that when I combine all those points together, I'll get a 0.
But why are these two equals, these summations?
Oh, because since the total summation is 0, then I can take all the negative ones and put them on the other side. Right? If you have a sum, you have, I don't know what, 3 plus 5 minus 7 plus 8 minus 10, I don't know what, equals 0. Then I can take all the negative guys, move them to the other side, and I say the positive guys equals the negative. But the negative, I'll change their sign. Right, I'll just take all those negative, pass them to the other side, they switch sign, and it should be equal. So that's how I got this equality. Yes?
How does HB call contradiction when you apply?
Because HB, I can apply it to this point. This is a point. Algebraically, it's just a linear combination of vectors. But a linear combination of vectors is a vector itself. So I can have my classifier and apply it to this vector. If I apply it to this vector, because it's a linear operation, I just take dot products, I can write it like this. I can push the HB to the xi's. And the assumption that HB gives me a positive sign for each xi in this set. So it's a sum of positive numbers. It should be positive. And I assume that HB gives me negative for every point outside B. And here I'm summing over the point outside B. And since this is equal to this, I have to get the same result. So it can't be both negative and positive. Yes?
Why can we assume then either whether HB applied to xi will give us all positive numbers or all negative numbers if we chose P and N based on whether A subscript I would be positive?
So first we chose P and N according to whether AI was positive or negative. Then we defined our set B. We defined our set B as the set of all points that got positive coefficients. Because if you shatter, you should be able to handle any set B. So I can choose the B that serves my argument. So I choose B to be all those xi's that got positive coefficients. And now there should be an HB that does it even for that B.
Oh, okay. Yeah.
Let me, for those of you that got completely lost in the algebra, let me give you such a geometric description of this, of what we've been doing here. Because geometrically, I mean, this is the end of the proof, if you haven't noticed. I mean, I have bad experience, not only with classes, but also with myself. I was teaching a course in which the proof was so heavy, it was automata theory, that I couldn't finish it in one class. So there were two directions, the if and only if. So I did the if in one class, and then I came in the next class to do the missing part. And as the time was ending of the class, I realized I was doing the same part a second time. And nobody in the class noticed. So if you haven't noticed, we finished our proof. Yes?
So if you prove that for any set of n plus 1 points, it cannot be shattered, is that sufficient, or do we have to prove it for any set greater than or equal to n plus 1?
Very good point. She asked, if I prove that every point or every set of size n plus 1 cannot be shattered, does it also show that no sets of size n plus 3 or n plus 4 and so can be shattered? I have two answers. First of one of them will be in your assignment, that it will be that if a big set is shattered, then any subset of it is shattered. The other answer is that I didn't use anywhere here that it was n plus 1 and not bigger. I just used that any set bigger than n has a linear dependence. OK? Now, I wanted to give you a geometric interpretation of what we did. OK? So the geometric interpretation is a very nice lemma, which is called, so let us think, for example, OK, let's consider 4 points in the plane. And let us look at half spaces without the restriction that they go to the origin. And I want to show that no 4 points can be shattered. So how am I going to show that no 4 points can be shattered? So there's this very nice lemma, which is called Radon's lemma. And what it says is for every n, And every x1 up to xn plus 2 points in Rn, there exists some subset B, subset of x1 up to xn plus 2, such that the convex hull of B intersection the convex hull of x1 up to xn plus 2 minus B is not empty. Okay, so now I confused you even more with this convex hull. What is the convex hull? I mean, I don't want to... Convex hull, if it takes a few points, is the smallest convex set that contains all of them. A convex set is a set that is intuitively convex, right?
This should be Rn plus 2.
What?
You x1 through xn plus 2
Yes.
in Rn?
Yes. Each point is in Rn.
Oh, okay.
I pick 4 points in R2. No. I picked 4 points in R2. What does it mean? If I pick 4 points from R2, I can pick this set as my B. The convex hull of B is this line. What is the convex hull? So this is the convex hull of B. What is the convex hull of the complement of B? These 2 points. The 2 convex hulls have a point in common. Or if I pick 4 points like this, what will be my B? I want a set such that the convex hull of this set and the convex hull of the complement intersect. So now if I pick B to be something like this, and the complement is something like this, they don't intersect. So how can I pick my subset such that they will intersect? The closure of B and the closure of the points not in B. You see what I'm trying to find? So what will be my set B? It cannot be 2 points like before. There should be a different arrangement. Anybody else that's not been so active so far? Yes. Right, I'll take 3 points. I'll have my point say this is my B. So the complement of B is those 3 points. Its convex hull is all of the triangle. It intersects the convex hull of B. So it tells you if you pick n plus 1 point, see this is 4 points in R2. It's n plus 2 points in Rn. If you pick n plus 2 points in R2, you can separate them in such a way that the 2 closures intersect. And that's what we did here. We picked, in some sense, we showed that there is a combination of these points and the combination of these points that give me the same answer. Right? This intersection is a combination of these 2 points. I can write it as a combination of these 2 points. And this intersection is a combination of these 2 points. So whenever I have too many points, I can separate them into 2 sets as the combination of one set and the combination of the complement intersect. Why is it bad for shuttering? Because if a half space puts both of those points positively, it should also put everything in between positively. And if a half space puts both of these points negatively, it should also put everything in between negatively. So on this point, the half space says it must be both positive and negative, and we get a contradiction. You see, we took our set, we divided it into 2 parts, and we showed that the closure of the 2 parts intersect. I can get a combination of P and a combination of N that give me the same result. But if I can separate them in the half space, all of these should be positive, including the closure. And all of these should be negative, including the closure. So if the closures intersect, there is a contradiction. That's a geometric interpretation of the algebraic proof that we just did. So our conclusion is that half spaces, homogeneous half spaces in our n have exactly VC dimension n. We showed that there is an n set which is shattered, the unit vectors, and no n plus 1 set can be shattered. So at this point, I feel that you are ripe to do assignment full of calculations of VC dimensions, and we can move on with learning. Yes?
In the algebra proof, is xi a vector or a real number?
xi is a vector. xi is a vector in our n.
So ai is also
No, ai is a real number.
So then the real number
Times the vector
is a vector.
is a vector. And the sum is also a vector.
So how can you say that a vector is greater or less than 0?
Note, it's not the vector is greater or less than 0. It's when the dot product. HB, x is a vector. Xi, x is a vector. It has coordinates. x1 to, so let's call it xi. So I have xj. I have the coordinates xj1 up to xjn. It has coordinates, right? And I have those vectors, x1 up to xn plus 1, and each of them is a vector. Now I take HB. HB is a vector of coefficients, w1 up to wn. And now when I apply HB to one of those x's, to xj, I get the sum, the inner product, of the w vector with the xj vector, which is just the sum, you see? It's the sine of the sum. I goes from 1 to n, the wi coordinates of the coefficient times the wi, the i's coordinate of xi. Now when I do this inner product, this is a real number. Okay? It was a vector, but with the dot product, it becomes a real number. In geometrically, it was a point in our n. But when I get here HB, it becomes either positive or negative. Okay? So I'm really having here an interplay between viewing those points as vectors in our n and viewing them as points to be shattered. Yes, Gerald?
Maybe I'm confused with something, but in Radon's theorem, you have n plus 2 points. And in the proof, you are proving that it is at least n.
Right, so let me just repeat the question. He's saying, oh, in the Radon theorem, I was talking about n plus 2 points. And here I was talking only about n plus 1 points. Where this discrepancy is coming from? And it's coming from that the Radon theorem gives you the VC dimension of general half spaces. And we only looked at half spaces that go to the origin. So they are one less in dimension. OK? There was another question somewhere here? Yes.
So that first equal sign on the equation on the bottom there, that's
Here.
not strictly true, right?
Right, it's the sign.
Okay, so you probably have to have a few more steps in there, right, to keep all the signs?
No, no, no. Yeah, what I'm saying is that if we had, we need to keep, we need to keep all the time, we need to keep those signs. HB is the sign. But to calculate HB, I do the dot product, and then look at the sign. So if I have two vectors which are equal, it cannot be that for one of them I'll end up with a positive sign, and for the other with a negative sign. Yes?
By the way, generally HB is a function, right? So you're identifying the function with...
HB is a function that operates like this. The function is defined by a set of weights, and it operates by, when you feed it any x, it does the dot product and takes the sign.
Yeah, but like up there we wrote HB is this, so basically you're identifying the vector with the...
Oh, HB is this. I identify HB with the vector of coefficients, right? Yeah. Okay, so I want to go back to learning. We had this, you remember that we had our fundamental theorem of statistical learning that says the VC dimension is important because it completely determines whether a class is learnable or not. So here we just did some exercise with VC dimension to show that we can even evaluate it for classes that are of high relevance in practice. Now we go back to the learning and to the relationship between VC dimension and learnability. So last time we saw that the statement that the class is learnable is equivalent to the statement that the class has finite VC dimension. This was only qualitatively. We want to give a quantitative strengthening of this theorem. So what I'm going to give now is a quantitative statement of the fundamental theorem. So what it says there is that let's write it like this. There exist constants C1, C2 such that for any class H of finite VC dimension, denoting the VC dimension of H by D, we get the following inequalities. So the first inequality, 1, I'm going to look at the Pak sense. So I'm looking to look at M. This is for every epsilon and positive epsilon and delta. I'm looking at MH in the Pak sense. How many samples do I need to epsilon delta learn the class H in the Pak sense, in the realizable case? And this will be above C1 D plus ln 1 over delta divided by epsilon, and below C2 D ln 1 over epsilon plus ln 1 over delta divided by epsilon. So what are we seeing here? I'm looking at how many examples do I need in order to learn my class with precision epsilon and confidence delta. And we see that this number is almost fully determined up to constant and this ln factor by the VC dimension. As the VC dimension grows, I will need more examples. This says I need at least so many examples, and I need at least so many, at most so many examples. And you see that they are very close. The gap is only the difference between the constants and this Lan factor here. So the VC dimension and the parameters of how precise I want my learning to be completely tell me how many examples am I going to need. This is for the PAC learning. And we have an even stronger theorem for the agnostic PAC learning. So C2, now I'm going to look at MH of agnostic PAC. How many samples do I need to learn in the agnostic model when I don't assume that the labeling comes from one of the functions in the class? And here I have an even more convincing statement. Here I have d plus ln 1 over delta divided by epsilon square. And here I have C2 d plus ln 1 over delta divided by epsilon square. So in the agnostic PAC sense, the only difference between the upper and lower bound is just the constants. Yes?
Should it be d 1 over epsilon?
What?
At the upper equation, you missed 1 over epsilon?
Where did I miss 1 over epsilon? Here?
Yeah.
No, I don't have a 1 over epsilon. Here it's very nice. This 1 over epsilon slack is only in the PAC sense. In the agnostic PAC sense, I don't have it. So let us just, yes?
So it's the same constant C1 and C2 in both of them?
And the same constant in both of them. Let us just look at a little bit at what does it mean. First of all, what happens if epsilon goes down? If epsilon goes down, I want to be more precise. Will I need more examples or less examples if epsilon go down? Yes? More examples. You see it from both cases. I divide by epsilon. So if epsilon goes down, this number grows. What about the dependence on the VC dim? If the class has higher VC dimension, the d appears in the denominator, I will need more examples. What about delta? Delta is the probability that I will fail in learning. If I want to make this probability small, do I need more examples or less examples? If I want to minimize the probability of failure, will I ask for more examples or less? Yes? Right. If not less, then more. Right. If I want to reduce my probability of failure, I will ask you to give me more examples. Because based on more examples, I can be more confident. And that's why the ln here is 1 over delta. As delta goes down, this number goes up. But it's only logarithmic dependence is not so effective. Now, what is harder? Is it harder to learn in the PAC model or in the agnostic PAC model? Is it harder to learn when you have a guarantee that one of the members of the class is a perfect predictor? Or is it harder to learn when you have no guarantee? Which one should be harder? Yes? Agnostic should be harder. And indeed, if I divide by epsilon square, say epsilon is 0.1. So here I have divided by 0.1. It's like saying I take this 10 times. But if epsilon is 0.1, epsilon square is 0.01. I take this 100 times. It's much harder to learn. I need more examples to learn in the agnostic case than in the realizable case. Right? And we have exactly the similar, I won't even write it, exactly the similar bound for the MH of uniform convergence, epsilon delta. Just to remind you, uniform convergence, the M of uniform convergence means what size of sample do I need to guarantee that the sample is epsilon representative. You remember we had like 2-3 lectures ago, we talked about epsilon representative sample. And this is the number of examples that I need for ERM to succeed. So this is MH if you want to work with ERM. You'll get the same thing. So this third line, the first two lines tell you both Pak and agnostic Pak are fully determined by the VC dimension. And agnostic Pak is harder than Pak. This line is also curious because it tells you whenever you can learn with ERM because you'll get uniform convergence. You will get samples that are representative. And whenever any algorithm can learn, ERM can learn with the same number of examples. So it's like saying machine learning is completely uninteresting. The only algorithm is ERM. Because this tells you whenever any algorithm can succeed, ERM can succeed with the same number of examples. The only difference is that we will have to somehow make this epsilon to epsilon over 2. I don't know if you remember it from our proof that if we have uniform convergence and we want to translate it into ERM success, we need to take a factor of 2 in the epsilon. But I can write the same equations because it's all swallowed by the C1 and C2. It's just the gap between C1 and C2. Yes?
It's the C1 and the C2 is the same C1?
Yes, same C1 for the three of them. Because you see, if I had here different C1s, then I'll just take the minimum of all three, and it will work for everybody. And if I had here different C2s, I'll take the maximum of those three C2s, and it will work for everybody. So I can just as well make it look more impressive and say it's the same constant for everybody. But it's just makeup. Yeah, what?
Just out of curiosity, do we know what the C1 and C2 are?
Yeah, we know. It's something like, I mean, it's the best C1. We want to make them as close as possible. Because the closer they are, it shows that we have a very good estimate. And it's something like 64 for some of them, 128 for another. It's not astronomically large numbers. That's not the crucial problem. Yes?
So if you take C1s and C2s as close as possible, then they're not going to be the same.
Yeah, if I take them as tight as possible, then they're not going to be the same. And I can't even make it completely tight. Here I even have this bothering gap of the land that I don't know how to get. We don't know yet whether it's really necessary or not. But the interesting conclusion here is that you see that if I give you a class and ask you how many examples will you need to learn it, all you have to figure out is the VC dimension, and everything else is already follows. Really, the VC dimension in a quantitative way tells you how difficult learning should be. So why doesn't the course end here? So there are two answers. I mean, one is that, courses in UW, they take 15 weeks. And or if I write a book and the publisher wants at least 300 pages, so I can't stop there. But there are more essential answers. And the main answer is that what we talk about here is the sample complexity. How many examples you need so that you will be, in principle, you will be able to learn. But in reality, when we want to do learning in reality, there is also a very important other component, which is the computational complexity. What do I mean by the computational complexity? Once you have seen so many examples, the VC dimension tells you how many examples you will need. Yeah, once you have seen so many examples, now you have to compute. Now, notice that this computation is allegedly very difficult because look at this. For example, we know that ERM always solves our problem. But what is ERM? It means go over all half spaces and find the half space that makes the minimum number of errors. How many half spaces are there? Infinitely many. How much time it will take you to go over all of them? Quite a lot. So it's not enough to tell you how many examples you need. When you have so many examples, if you magically can find the best classifier in the class, you are done. But this magically, if you want to turn it into an algorithm, may take us a lot of time. So in principle, if someone gave me a kind of an oracle, that I'll give him a sample and he will tell me what's the best classifier in my class for this sample, I will be done. But the search for it, if I try to go one by one over all hypotheses and for each of them evaluate its error until I find the one with the minimum error, it will take me a lot of time, and that's a crucial component. So we completely ignored so far this aspect. So what we're going to do next is, first of all, we talk about the proof of this theorem. So if you're afraid of proofs, skip next lecture. And then we will talk about the computational complexity, which is a very important component of machine learning.